Good morning, class. Today we will discuss the next topic of this chapter, that is your electric field due to a uniformly charged thin spherical shell, or you can term it as hollow sphere also, right? What you have to do is you have to calculate the electric field for the various cases. That means if the point lies inside, if the point lies outside, if the point lies somewhere at the center, then what have happened to the electric field. So let's discuss some case. Now the first one is your sphere. Let's take a sphere. This is your sphere and here is its center, that is point O, right? Now the charge is uniformly distributed over its surface in this manner, right? Now if the charge is distributed like this sphere has some radius, let's say that is your capital R. As the charge is distributed along its surface, so the imaginary Gaussian surface is to be made somewhere in the form of dotted line. Let's say this is your Gaussian surface. Now what happened, let's say this Gaussian surface, we have to take a small elemental portion as we have done in the previous derivation. So that's in the similar manner we are taking the elemental portion. Now this elemental portion, let's say that the point P where you have to calculate the electric field is somewhere lies on the Gaussian surface. Now this point has a distance from the center of the sphere, that is your R. Now electric field due to the positive charge is always ejection out, so that's why it is somewhere like this. And what is the surface area vector? It is also going outward in the same direction. Both are in the same direction, so that is one thing is clear, that theta is here 0 degree. Okay, so what we have considered the charge q over a shell, right? So that radius r is more than that of the radius of sphere. This is the distance r, right? Distance r means the distance of the point O to the point P where we have to calculate the electric field. Now we have to calculate the electric field at this point. This is the point P. Now by Gauss law, because it is the application of Gauss law, so we have to apply Gauss law. By the Gauss law, what is the flux? That is your integration around the closed surface, let's say S, that is your E dot ds, and that is q over epsilon naught. This is the definition of the Gauss law. Because the electric and the ds vector is in the same direction, so that's why theta is 0 degree. So we will write here as E ds cos of 0 degree, and that is q over epsilon naught, right? Cos 0 is 1, so that's why final expression we have E ds, that is q over epsilon naught, because it is a Gaussian surface, and in the Gaussian surface the magnitude of the electric field is constant, so that's why it is always taken out of the integration. So what we have, E, and this is your curl vector ds, and this is q over epsilon naught, right? Now this is the sphere, and sphere have the surface area that is equals to 4 pi r square, right? So that's why q over epsilon naught. Now what is the electric field? Our aim is to calculate the electric field here, so electric field remains here on the left hand side and all things will be taken on the right hand side. So what we have, this is like this. This is your final expression. So electric field, the expression of the electric field tell us that it somewhere resembles from the electric field intensity due to a point charge. Right, now this is the final expression we have got for a spherical shell or a hollow sphere electric field, right? Now we have to discuss cases, right? First point what we have discussed here is the case when the point is lying somewhere outside the shell. Here the point lies outside the shell, right? Okay, this is the first case what we have discussed, and we find that the electric field in this case will be equals to 1 over 4 pi epsilon naught q over r square, that is exactly equal to the electric field intensity due to a point charge, right? Now case 2, that is electric field at a point on the surface of a shell. If this point lies on the surface of shell, what happened to the electric field? These are the certain cases we have to discuss here, right? Now let's see how it goes. Let's see that is your sphere. Now in this case, this is the center of the sphere. Now the point lies somewhere on the surface of the shell. So that means here the point lies. So if it lies here, the electric field obviously due to the positive charge will be like this, right? And then what is the area vector? Now area vector is also along the same direction, ds. This is your electric field, this is your d. Again theta is 0 degree. Now if this is your radius of the sphere, that is your capital R. If the point P lies on the sphere, then that is our small r will exactly becomes equals to the capital R, because they have the same distance. This r is also becomes the radius, no? So that's why r is also equals to r in this case. So what happened? All the equation will remain same, only the small r is being replaced by capital R. So what is the electric field in this case? That is equals to 1 over 4 pi epsilon naught, and that is your q over r square, in this way, right? Now because this charge is distributed over its surface, so sigma means surface charge density. Surface charge density is q over area. So area of sphere is 4 pi r square, right? So what will be the q? Q will be equals to sigma 4 pi r square, like this. Because here r, small r is capital R, so that's why we will replace it by capital R, right? Now we just put the value from here to here. So what we have electric field that is equals to 1 over 4 pi epsilon naught. Q कितना है? What is the value of Q? Q is sigma 4 pi r square. And what is downward? It is r square. Now cut this will also be cut. So what you have electric field is equals to sigma over epsilon naught, what we have discussed in the previous derivation also. Whenever there is a sheet having a finite thickness, then the electric field is this. And in this case, when the electric field, you have to calculate the electric field of a point that lies somewhere on the surface of a hollow sphere, then in that case the electric field equation is sigma over epsilon naught, right? Now the third case we have to discuss. What happen if the electric field we have to calculate the electric field at a point inside the spherical shell? What happened in that case? Let's do it. We have to calculate the electric field, right, for a point inside the shell. Right, now what happened to the point? The point lies somewhere inside the shell, not on the surface of the shell. So let's see how it begins. Let's say this is our sphere, this is our Gaussian surface over here. Now the point P lies where? Inside the shell. Inside the shell means, let's say that here it is, right? This is your point P. I have written here but mentioned here, right? So what is the area vector? Area vector again goes like this. This is your capital R and this is your small r. So r dash, we will represent it by r dash. Obviously r dash and r may say which one is bigger. So obviously r is bigger, right? Again you want to write the flux along a closed surface, so that's why E dot ds, that is q over epsilon naught, right? As the Gaussian surface encloses no charge. Now in this case, whenever the point lies inside the shell and